Well, now let's look at some uneven cash flows, not an annuity, but payments that have different values. And here we're going to calculate the future value of 3 payments, deposits into an account, if you'd like to think about it like that, of 300, 600, and 200. So how much are we going to have in the account at time 3 if we're earning interest at a rate of 10% compounded annually? Well, that $300 spends 2 periods in the account up to time 3 here. So there's our compounding factor there. The $600 deposit earns interest for 1 year, so that'll be another $60 in interest, right? And then that $200 is deposited at time 3. So that's the time 3 value of that. So now we can add up these 3 future values and get the future value given that those 3 deposits are made into an account, 1223. So there's each piece on the calculator. Notice the last one is a time 3 value, that last deposit, so we don't have to compound that at all. Now, if we've got those same uneven cash flows and we want to say, well, what's the present value, or put a different way, how much would I have to put in the account today in order to make those 3 withdrawals and just exhaust the account? Well, the idea is the same. We're going to take the present value of each of those 3 and add them all up to get $916.86. Discounting the $200 for 3 periods, the $600 for 2 periods, $300 for 1 period, and summing them all up. And those are just the calculator strokes for calculating those present values. Okay, let's look at the effects of compounding frequency. Compute the future value 1 year from now of $1,000 using a stated rate of 6% with annual, semi-annual, quarterly, monthly, and daily compounding. So this is a review of what we looked at a little bit earlier in this reading to do with the effective annual rate. So our $1,000 at 6% annual compounding grows to $1,060. With semi-annual compounding, remember if our stated rate is 6%, for semi-annual compounding, we're going to divide that by 2, so our interest rate is 3, and we've got 2 periods. And notice we didn't put payment in here, but payment is 0. So if you cleared the work, that'll set the payment to 0. If not, probably best practice just to put that payment in as 0 so you explicitly note and remind yourself what's going on. So with more frequent compounding, it grows to a bigger number, just as we saw with our effective annual rate was greater the more frequent the compounding periods. So with quarterly, we divide that stated rate by 4 and use 1.5% interest rate for 4 periods. Monthly, we've got 12 periods. Our effective monthly interest rate is 0.5. And with daily, assuming a 365-day year, we've got n equals 365. Our daily effective interest rate is 1.64%, and we get a future value of $1,061.83. And I may have misspoken right here because we're putting that interest rate in as a whole number. Our daily rate is really 0.0164%. 6 divided by 365. Here's another example. Compute the present value of $1,000 to be received 1 year from now using a stated rate of 6% with annual, semi-annual, quarterly, monthly, and daily compounding. Well, now, with more frequent compounding, the effective discount rate over the year is higher, and we're going to get smaller values going back the other way. So the present value of that 1,000 is $943.40 if we've got 6% with annual compounding. With semi-annual compounding, remember that makes our effective annual rate a little higher, so our present value is going to be a little lower. And then as we use those same terms we did before for quarterly, monthly, and daily compounding, and notice these are pretty darn close together, but they're still getting smaller when we move from monthly to daily compounding, or actually discounting in this case. So again, n equals 365, our interest rate is 0.0164%, and we compute the present value of 941.77, and in each case, we're implicitly saying that the payment here is zero. There's no money in or out of the account over this 1 year period. Well, we can also use those time value of money keys to calculate any of the five, right? Because we've got N, we've got our interest rate, I over Y, we've got future value, present value, and we've got our payment. So here we're going to put in 4 of those and calculate the payment. We have an expected rate of return of 7%. How much must be deposited at the end of each year for the next 15 years to accumulate $3,000? So in this case, we've got 15 years, so N is 15. We've got our discount rate, our interest rate, of 7%. Our present value is 0. Our future value is $3,000. So we calculate that payment, and we do get a negative value, because if we want the future value of $1,000, we got to pay in $119.38 at the end of each year for the next 15 years. So we solve for payment, and again, this is in end mode here. Well, let's calculate payment once more for a $2,000 13-year loan with equal end-of-year payments and an annual interest rate of 6%. How much will the payments be? So this isn't like our bond where we had interest payments and a maturity value or face value paid at the end. These are going to be equal payments to repay this 13-year loan. So we've got 13 payments. We've got an interest rate of 6%. The present value, that's how much we borrow today. And we're calculating the payments we're going to have to make to pay this back. We call this a fully amortizing loan because the future value is 0. It's like typically on a home loan or a car loan, you make level payments, and when you make that last level payment, in this case, payment of $225.92, that settles the loan. There's no extra payment at the end. So both the interest and the repayment of principal are in this payment of $225.92. And if we put in 4 of them, but not N, we could calculate N. So we'll do it here. It's kind of maybe a stretch in terms of a problem you might run into, but how many $100 end-of-year payments are required to accumulate $920 if the discount rate or interest rate is 9%? Now, we put in the interest rate, the present value is 0, the payment's minus 100, and we know the future value. We want to accumulate 920. So we compute N. Here we get 6.9998. Now, if you're using the HP12C calculator, it rounds it up to the next whole number. Really shouldn't be a problem on the exam, because certainly the exam writers know that. They're not going to try and fool you between which calculator that you use. But just remember that on the TI calculator, it'll give you fractional or decimal periods here, 6.9998, real close to 7. The HP12C will give you 7. If N is anything greater than 6, it'll round that up to the next whole number. Let's look at one more example on calculating N here. A $1,000 ordinary annuity earns an 8% return. How many annual $150 withdrawals can be made? So let's look at our input numbers here. We've got a present value. It's a $1,000 annuity. We're going to buy it today. And the question becomes, we're promised $150 payments. How many are we going to receive if the interest rate is 8%? So our present value is our deposit here of $1,000. The payment's minus $150. Our interest rate is 8%. And our future value is 0. Once we get that last $150 payment, that's it. No more. So we can calculate N here, 9.9029. So just about 10 periods. And here we can calculate the interest rate given the other 4 inputs. An investment of $100 at the end of each of the next 5 years, that looks like a 5-year ordinary annuity, will be worth $600 at the end of the 5th year. What's the annual rate of return being earned here? Well, taking a look at our timeline, we see our future value is $600. In end mode, we've got 5 $100 payments. So there's our payments minus 100. Our future value has to have the opposite sign. If we're going to put the payments in, we're going to take the 600 out. If we're going to take the hundreds out, we'd have to put the 600 in. It'd be like a loan. But in this case, it's going to be worth $600 at the end of the 5th year. So we're in end mode because we want our future value to be right there. We want our payments at the end of each year, and we compute the interest rate. And the interest rate being used in these calculations for the future value of those $500 deposits, 9.1281. So I think we've covered all 5 of these now. Putting in 4 of them, you can solve for the other one. But clearly you've seen by now, understanding the problem and getting it set up right, and it often helps to use a timeline like this, especially when you're first working with these problems. The timeline, where are the cash flows, what am I looking for, then which tools are going to get me there. Let's take a look at one more here. A $700 deposit today will buy an ordinary annuity that pays $100 per year at the end of the next 10 years. What is the rate of return? Well, let's look at our calculator inputs here. Certainly N is 10. We're in end mode. The payments are at the end of each of the next 10 years, so we're in end mode. Our present value, that's the amount we pay out today, so we put that in as negative 700. The payments are positive. That's what we can withdraw. There's no value at the end, so we've got our 4 inputs. Compute the interest rate implicit in those numbers, and we find that it's 7.0728%. Another example, funding a future liability. You must make 5 annual $1,000 payments, the first one beginning year 4. To accumulate the money to make these payments, you want to make 3 equal payments into an investment account. The first one is to be made a year from today. Assuming a 10% rate of return, what is the amount of these 3 payments? Well, let's break this down a little bit. We want 5 payments of $1,000. And the first one, beginning of year 4. Well, the beginning of year 4, that's time 3. The end of the 3rd year is the same as the beginning of the 4th year. And we want to make 3 equal payments into an account. The first one to be made 1 year from today. So this is a little bit like a retirement planning problem. How much do we have to deposit into our retirement account for this many years in order to make withdrawals at retirement of this amount for this many years? Now, this is a little simplified, but it's the same idea and the same solution technique. So it's really going to help, I think, for you to put this on a timeline. So we've got a payment starting at the beginning of year 4, which is the end of year 3. Here's the 4th year right here. So this is the beginning of the 4th year. And we've got $5,000 payments beginning then. So what we're going to do is, this is like the deferred annuity that we looked at. We're going to calculate the value right here and then figure out what deposits we'd have to make. I guess we'll calculate the value right here because we've got 3 equal payments, and we're going to make those payments here, here, and here. So the future value of these 3 payments is going to be the same as the present value of these, 5 payments. So, and since we want the value right here, I think we're going to have to put that in begin mode to get that. So the amount needed at time 3, that is the present value in begin mode of those 5 payments, is $4169.87. If we have this amount deposited right here, we can make these 5 withdrawals at an interest rate of 10%. So now the question becomes, what deposits do we have to make for 3 years in order to have this value in the account at time 3? So now we're going to go in end mode because our future value is going to be on the date of that last payment. So n equals 3 now, interest rate's 10%, present value is 0, there's nothing in the account to start with, and if we make deposits of $1259.78 here, here, and here, and earn 10% in that account, then the value at time 3 is going to be the $4169.87 that we need to pay for those $1,000 deposits that we calculated the present value of previously, and we did that in begin mode. The cash flow additivity principle is something we've already seen and we've already been using. It just says the present value of the sum of 2 future cash flows in the same period equals the sum of the present values of the 2 cash flows. Doesn't matter how you break it up. If you take the present value of $100 3 times, you got the present value of $300. As an example, cash flows of 100, 100, 400, and 100 in the next 4 years. We could break this up into 100 and a 300. So now we can calculate this as a 4-period annuity of 100 plus that extra 300 that comes right there. So here's the annuity, the $100 payments. So we can calculate that, and then we've got an extra $300. And that extra $300 comes at time 3, so we calculate the present value of that as well at $225.39. And if we add those up, then we've got the present value of those 4 cash flows. So we can break these cash flows, future cash flows, up into any amounts we want for our calculations. Just make sure that we've added the present value of all the various pieces that we may have broken it into. So a total here, $542.38.